Greetings, let's prove this theorem regarding the limit of a function going to a and also going to b, that it implies that a equals b if, of course, they approach with the limit the same value c, and that c can be from real numbers or infinities. But anyway, let's prove this. We'll do it by contradiction, so I'll suppose that a is not b. And I also take for the whole time some epsilon higher than 0. By the way, epsilons or deltas, when I'm now using them, I always mean they're real. I'm not going to be explicitly noting it, but let's just take this whole time as real. I'm just going to be mentioning that the epsilons and deltas are above 0. And by the way, also I recommend to know the idea of neighborhood first. Maybe perhaps the notation I'll be using for neighborhood is not common, it's not familiar with everyone, but when I say neighborhood, I really just mean neighborhood around that point, nothing more than that. I mean really just the interval, for example, neighborhood around point c by epsilon, I mean c minus epsilon until c plus epsilon. Alright, and then also we'll be using two notations for neighborhoods. The one with p will mean exclude the point around which is the neighborhood, and the one with b will include the point around which is the neighborhood. But that's a small detail. But anyway, let's suppose that these two limit values are not equal for the sake of contradiction. And then we should have the neighborhood around, then the intersection of the neighborhood around a by epsilon with the neighborhood around b by epsilon should be an empty set, because if these two limit values are not equal, then the intersection of their neighborhoods should be empty. And then let's say there exists some delta 1 higher than 0, and for that we have for any x inside the neighborhood around the point c, which is the limit input value by delta 1, we have f of x falls into the neighborhood of the first limit value a, the output. And then there also exists delta 2 higher than 0, that for every x in the neighborhood of c by delta 2 this time, f of x will this time fall into the neighborhood of b by epsilon. So the a, b are the limit values, the output limits, and c is here in the p labeled neighborhoods, which exclude the point c itself. And delta 1, delta 2 are differently for the final a and b, because we suppose they're not same, so we suppose them as separate cases. And the next step is to take max of delta 1, delta 2 to yield a delta that applies for both sort of safely. So I'll say delta is the max of delta 1 and delta 2, so a new symbol delta. And then for delta, it should apply both things at once, what apply for both of these two lines. So for x in the neighborhood of c by delta, which is by both delta 1 and delta 2 conditions satisfied, we will have f of x in the neighborhood of not only a, but actually intersection of both a and b's neighborhood, because we want to satisfy both at once now by the new delta. So they should be in the intersection of the two, in both neighborhoods. But these actually are equal to the empty set by what was yielded when we supposed a doesn't equal b, so we contradicted it hereby. We said f of x belongs to empty set. So that's contradiction. And thereby we contradicted this initial assumption, and thereby we proved the theorem that a is b, if a doesn't equal b was contradicted.